Yeah, so as I said before, today's class is going to be three things. The exam review, going over homework questions, going over the class project, and then new material if we have time. So the first question was on the format of the exam. So a typical format of the exam will have 4 or 5 questions, and each of the questions will have multiple parts, kind of like your homework problems. In addition, there will typically be 1 extra credit question. The extra credit question is an opportunity for me to give you what I perceive as a challenging question, and to challenge the students who find the other problems easy. But I make it extra credit so that it doesn't penalize others. So the questions will be a combination of questions that you have done in the homework. So some questions that will be similar to homework problems that involve calculations. Those are typically the problems that students do okay on. I won't give you exactly the same problem. I'll give you variants of the problem. But the idea is if you've done the homework problems, then you should be fine on that section of the exam. The next, some of the questions, at least one question is a whole bunch of short answer questions, or the short answers are kind of split among the questions. And so these short answer questions are conceptual questions. So you'll write like a 1-sentence response or do like a very simple calculation to answer it. Sometimes I have like true, false type things. So sections of the class where we didn't have substantial homework problems, but we discussed a lot of concepts. So the things that comes to mind is like module 2, when we talked a lot about the Schrodinger equation. You guys didn't do a lot of solving of the Schrodinger equation, but there were a lot of concepts there. So sections like those, you can expect to have conceptual questions on those sections. So for that, since there's no homework problems to study for it, what I would recommend is go over the lecture notes and quiz each other on it. Like if someone can quiz you on, or if you're studying in groups, if you're working together, quiz each other on the concepts. And if you were teaching the class yourself, what kind of questions would you try to come up with to test understanding? Those are essentially like the types of questions that I would put on there too. So again, 4 questions, 4 to 5 questions and 1 extra credit, and each question will have multiple parts. Now the content of the exam is going to be modules 1, 2, 3, and 4. Module 1 was the crystal structures. Module 2 was the things on where we learned about the wave and particle-like nature of electrons. We talked about Schrodinger Equation. We talked about the Bohr model. In module 3, we started getting into doping, the actual semiconductors. So we started off with what happens when you put atoms together. How does that change the Schrodinger equation? And we found out that there are energy bands. So being able to draw energy band diagrams, being able to explain what they are, being able to understand what energy bands are as opposed to discrete energy states. Then we got into what happens when you dope the material. We talked about intrinsic versus extrinsic semiconductors, calculating carrier concentrations, and drawing the band diagrams of intrinsic and extrinsic semiconductors. So if I give you a band diagram, you should be able to tell me the carrier concentration or the doping concentration. If I give you the carrier or doping concentration, you should be able to draw the band diagram. Okay. The problems that you've done in the homework are probably with silicon. If I wanted to make sure that you understand conceptually what's happening, I could give you a harder problem on a different material that you haven't seen before. But if you apply the same concepts to it, you could do fine on that. That's module 3. We started getting into calculating the resistivity of materials and the contributions of carriers in each one. And we talked about what drift current is. We talked about current densities. We talked about the velocity at which carriers move through the material. We talked about different scattering mechanisms, which results in resistance. And then we talked a little bit about the energy band model for drift currents. And then Module 4 was excess carriers, and we talked about the 4 parts of the carrier life cycle: generation, recombination, drift, and diffusion. So there are a lot of homework problems on Module 4, a lot of quantitative calculations that you can do, and you can be assured that there will be at least one problem like that on homework 4 on this test. Okay, so I do like to do like a roughly equal distribution. So if we have 4 modules on the test, there's a good chance there'll be somewhere around like, 1 question each. Something like that. I try to make my tests so that if you have a basic understanding of the material, you will get, you'll get your points for that. There are some questions there that are designed to be more challenging, and that's to help, otherwise everyone will just get like 100% on the test, which is not bad. But at the graduate level, especially, I want you guys to demonstrate a little bit more in-depth understanding of the material. So there'll be some more conceptual questions, more difficult questions than there would be at the undergrad level. But the main content, I would say, is fairly similar.
If you make a mistake in the calculation, how much you gonna lose? How much point you gonna lose?
Yeah, that's a good question. So the way I do the grading in the quantitative, in the calculations, I look for process. Okay. If you know the steps of the problem and you show the steps of the problem, but you happen to have some of the numbers wrong for simple calculation errors, then I won't take much off. If you have the wrong answer, if you have the right answer, but the steps don't show you leading to the right answer, then that's a real problem. You won't get the points on the problem, and I'm going to wonder how you got it. Okay. If something in the middle is, let's say you get the wrong answer, and it's a calculation error, but that calculation error is something that shows that you missed an important aspect of the class. Like some type of calculation that you should know that is fairly straightforward to do, or if your units are like totally off. If you're getting, a carrier concentration of like, 10 to the 50th. Then you should know that like something's amiss, and you can even indicate that on your test. Like, I know this answer seems to be off. I'm not sure where I did it, but here's the step. If you show the steps, you'll get partial credit for it. The grading of the exam, most likely I will do all the grading myself. Once in a while, like in the past, like with undergrad classes, when I have a lot of students, I sometimes grade some of the problems myself and have some of them done by a grader. I probably will end up grading most of the questions myself in the class. So when you do the answers to the questions, make sure you write neatly. I know that's it's a picky point, but it's important. If I can't read your writing, I can't grade it. And the natural instinct is to grade, is to mark points off if you just don't understand what's going on. So please do write neatly on the test. In terms of other policies, as you know, you're allowed 1 page of notes front and back, and you're allowed to bring a basic scientific calculator. No phones, nothing with any kind of wireless on it. You'll be asked to put your phones in your backpacks at the beginning of the exam and leave your backpacks on the floor. So if you don't already have a basic scientific calculator, you can get them on Amazon with 2-day shipping. They're also available at Meijer or Target, whatever.
So a TI-83 we wouldn't be allowed to use it?
A TI-83 is what, the programmable?
I think so, yeah.
Does it have Wi-Fi on it? Does it have wireless?
No, not the one I have. I don't know if it does now.
Does it have memory? Can you pull up files in it?
Files, I don't think so, but I know you can program it. You can download things to it.
Can it display images and files?
No. And I think I meant to say TI-86, but I don't think it has that capability.
So my 84 can do that? I have no idea how to do it.
I like having 84.
It'll be complicated to.
Yeah, I don't think we can see.
I would rather just learn the material than try and figure out how to choose.
Yeah, I know. That's what I tell the students. I mean, if you have a calculator that's questionable and you just want to play it safe, I would just recommend just getting a basic scientific calculator. You've done the homework problems. You don't need a fancy calculator for any of that.
But I only know how to use the fancy
calculator. You don't know how to use the basic. It wouldn't take you very long to learn it. I mean, they're extremely simple. Maybe they're too simple for you.
So is that a yes or no on the 83 and 84 calculators?
I think, the TI-83s, are they the ones, or the 84s are the ones that you can download images?
I don't have any idea, though. That's...
You can pull up images, so it's not like you can download the textbook or something like that. But
You can't web search on it or anything.
Yeah.
There's probably calculators.
I think you can do that with the 89 Platinum, but I don't think you can do
there's new ones where you can actually download images.
84.
Is that
Okay.
what you're thinking of as not good, or?
Well, can you save files and images in there?
I don't know.
Nobody knows how to use it.
I mean, we could Google.
I would honestly if there's question marks here, just use a basic scientific calculator. I'd appreciate that. It would just make things, give it a level playing field. Right. Yeah. I know that sucks for people who spend a lot of money on calculators, but it's just to level the playing field. All right. Shall we get into? Are there any other questions about logistics of the exam?
How long the exam will be?
It'll be during class on Monday, just during the regular class period. So we'll start at 5:30. The exam will end at 7:10 for everybody, just to be fair to everybody. Yeah, I will be out of town, so there will be someone proctoring the exam.
How many questions should we expect on the exam?
There will be 4 to 5 questions and 1 extra credit.
That's it?
Yeah, but each question has multiple parts.
Has 10.
Each each question has multiple parts to it.
How many conceptual questions can we expect?
I think either a 50-50 mix, or maybe a 60-30, 60-40 mix of homework type problems versus 30% conceptual questions. Yeah. And DeMarco, you've been in one of my classes before, so the conceptual questions typically are the harder ones.
I remember on the final you gave us all conceptual questions.
Yeah, and a lot of students didn't like that. They weren't.
Tough. I mean, you can't get partial credit with the conceptual questions. Either you know it or you don't. So. Yeah.
Well, some of them you can. If it's a 3-point question, and I see that you in your answer you demonstrated some kind of understanding of it, then I'll give partial points. Yeah, but if it's a true or false thing, I mean, I usually try to have some kind of explanation in there so that you can get partial credit if you demonstrate some understanding of it.
Professor,
Yeah.
question. Would the final exam be combined, cumulative of mid 1 and mid 2?
The final exam, which is going to happen in December 11th, I have a feeling that, because we're already a little bit behind on class material right now, the final exam is probably going to be mostly on the stuff you haven't been tested on yet.
Module 5 till module 8.
Well, there's a second midterm. There's a second midterm coming up in November.
In November? Can you know the date?
The schedule said 1 midterm and 1 final on the syllabus.
There isn't midterm.
I thought the syllabus said 2 midterms.
It's just not on the schedule.
Oh, it's not on the
Yeah,
calendar.
that's what I looked at. Not on the schedule,
The
yeah.
other exam isn't on the calendar, but it is on the syllabus.
Oh, I didn't put the date. I didn't put the date on the syllabus. Right.
Oh.
But you said something about November 20th.
That's what I was planning on having it just before Thanksgiving, which would give it would end up being mainly on diodes and a little bit of MOSFETs. That's the plan. And then if we did that, then the final exam would be on just the material that we cover after that, the end of MOSFETs and maybe a little bit of.
Three midterm, like this.
Well, the final exam is worth more than the midterms. That's what's stated in the syllabus. But the final exam is not, to answer the question, the final exam is not going to be like totally cumulative. Most of the emphasis is going to be just on the newest stuff. Because the reality is that the newest material, it actually requires you to know all the stuff that we did previously in the class. Yeah, sorry for the calendar thing. But the plan is to have like the two midterms in the final.
Are we going to talk about the projects, or you did that on Monday?
I was planning on talking about the projects later today.
Okay.
Yep. So shall we go over homework questions first and then get to the project questions? And then if we have time, we'll cover some new ground. All right. All right. So questions on the homework. Let's, should we start from the most recent or the oldest homework?
The oldest.
Oldest homework, okay. All right, modules 1 and 2. Hopefully everyone can see this. Okay. So let's just start with questions. Were there any problems that were problematic on this first homework?
Did you ask for different planes other than
Okay, so the question is, will there be questions on different atomic planes? Yes. Yeah, I would expect you to know the 3 crystal planes, which are most common in silicon, which is the 100 family of planes, the 110 family of planes, which is actually in this test question, and there's also the 111 family of planes. 100 is the easiest. The 110 is a little bit more than that. The 111 is I would say the trickiest. But I've had questions on all 3 in the past. So this question, since we're talking about this one, it's about atomic distributions. This is a good test question to have because it requires you to do some calculations. You have to have some conceptual understanding of atomic distributions, and that's really what Module 1 is all about. So the types of problems that you can expect for Module 1 will be, something like calculating volume density, calculating surface density, drawing the distribution, calculating spacing between atoms and such. Yeah.
So would we have to have memorized the different atomic structures, like face-centered cubic versus diamond lattice versus square lattice?
Yeah, I would expect you to know that. Remember, you can bring 1 page of notes front and back.
Okay.
Right. Oh, by the way, I mentioned at the beginning of the semester, but the notes that you bring to the exams should not be photocopied. I would suggest, handwritten notes are fine. And you will be turning in those notes with your exam. You're required to do that. What I don't want to see on the notes is just like a verbatim copy of like homework solutions and things like that, because that's not really demonstrating that you understand the class material. What's better that I'd like to see is like just notes of concepts and things like that, like what David mentioned. Like if you jot down the differences between face-centered, body-centered, diamond lattice, and so forth. So what happened one year is that a student actually spent a lot of effort in taking, this was during the final exam, somehow they shrank down all the lecture slides from all the modules. And I have a lot of lecture slides, right, for every module. So like you imagine like 50 slides per module, and there were like 6 modules in the class. There's like 300 slides that were like progressively photocopied smaller and smaller. I think you went to Kinko's and gave them a project to like figure out how to do this. And the entire semester was on there. And so I was impressed that he did that. But I was like, if you spent that time studying, I think you would have done, it would have been time better spent,
I know it's student who did like a better job than this. He used like the needle instead of the lead, and he graved a pen with the needle.
Oh wow!
And each pen took 1 hour and a half.
Oh my gosh!
And he had like a dozen for each like subject.
That's amazing.
Wow.
I mean, that takes a lot of.
Is it easier to grave like take you 1 hour and a half to grave this pen and then just to memorize it? He said, no, I don't want to memorize.
Well, props to him for
I'm sure you could sell those.
putting that much effort. Yeah. But yeah, honestly, I feel the best use of time is just to go over homework problems, go over the lectures. You know, listen to some of the lectures again if it's helpful. If you can work together in groups, it's also a great idea. Explain concepts to each other, especially the conceptual sections. I recommend that if you have the ability to work with folks in the class. So in Module 1, this is something that I would expect you to be able to know, how to calculate these area and surface densities, volume densities, just like the basic atomic structures that we talked about. Keep in mind, Module 1, at the end, we also talked about the atomic structures of things like graphene and carbon nanotubes. We talked briefly about like that, the trigonal planars, the 2D and 3D structures. We talked about Lewis diagrams and the bonding between the atoms. Yep.
If you change the silicon to another atom, finding the how much atom in the spatial plan is so hard. For example, question 1, part C.
Mm-hmm.
I think the shape of atom.
I'll calculate the surface density of atoms. Mm-hmm.
If you change it to another atom, I think we cannot find the.
If we change to another atom, it depends on how the atom bonds. Yeah, so we've only talked about a few examples of bonding in this class. We've talked about tetrahedral bonding, which is what silicon does. Each silicon atom bonds with 4 other atoms around it. So if I gave you another atom that also does tetrahedral bonding, you should be able to figure it out. Right? Like if I said, like, let's say carbon or germanium, they're all column 4 elements. And so they do tetrahedral, similar types of bonding, right? I could also say, like, hey, let's say you have graphene, which has a trigonal planar, planar bonding. Figure out the area density of atoms in that, something like that. So I'll generally will just do the types of bonding that we've discussed in the class. If I won't give you something like, here's a lattice made out of Einsteinium, unobtainium. Like, figure out the crystal structure for that. I won't do that. So this homework was on modules 1 and 2. So this is talking about, this next question was on the Bohr model of hydrogen. There were a lot of questions here on, a lot of concepts here on the Bohr model. First of all, it talks about discrete energy states. Discrete energy states have discrete energy transitions. When there is a discrete energy transition, a photon is given off, and that photon has an energy equal to the energy transition. Right? So there were a lot of concepts in this type of a Bohr type problem. So I expect you to know that. Are there any questions on the homework on number 2 that you all would like to go over? Feel free. If you have questions on it, now's the time to ask.
I have a question for number 1.
Mm-hmm.
I think it was letter D. Yeah, the last one. Yeah.
Mm-hmm.
I didn't quite understand that. Well, difficult for me to solve.
Okay. All right. Let's look at the solutions then. The area density of the 1, 0, 1 and the 0, 1, 1 planes. DeMarco, were you able to do part B?
Yeah, that wasn't too bad.
Okay. So the thing with part D was that because of crystal symmetry, the area density of atoms in the 1, 0, 1 planes and the 0, 1, 1 planes will actually be the same as the 1, 0, 0 plane.
Oh, because
And-
it's in the same family. Okay.
It's in the same family of planes. You got it. And just to hit that point home, I'll let me just pull up the solutions here. So this is the 110 family of planes. This is the silicon lattice here, the diamond lattice, and the 100 plane cuts diagonally across here, diagonally across the cube. And so what the atoms look like as you cut across here is like this. Notice that this is A, this is the edge of the cube, but because we've cut diagonally across it is A times square root of 2 at the bottom here. And then the distribution of atoms you have here, this part is straightforward. You have the corner atoms here. There's the 2 atoms that are on the face. This is in the middle of the face. These 2 atoms are in the middle of the face. And the tricky part were these interior atoms. 2 of the interior atoms exist in this 110 plane. And the other planes, the other planes that are in the same family, the 101 and the 011 planes, will all have the same area density because of the symmetry of the diamond lattice. Hello, Dominique. How are you? All right. Okay, so that answers your question, I hope. The de Broglie wavelength. Now, you can certainly expect conceptual questions on Module 2. This is an example of a calculation of just understanding what the de Broglie wavelength is. But one of the key concepts that I wanted you to get out of this question was the fact that the de Broglie wavelength only becomes important when you're dealing with very small objects moving at very fast velocities. So here we're comparing the wavelength of, we calculate the de Broglie wavelengths of a 12 kilovolt electron. We're comparing with visible light. Both of these things have, de Broglie wavelengths that we can calculate and are not too small. Some of these other examples, like if you calculate the de Broglie wavelength of a 1,000 kilogram car that's moving at this speed, a smoke particle moving at with a mass 10 to the negative 9 grams traveling at this speed, they have de Broglie wavelengths which are like 10 to the negative 34, or 10 to the negative like 28, something like that. Extremely small de Broglie wavelengths. So there's no way that we can measure or use that de Broglie wavelength in any kind of form. When the mass of the particle becomes super small, like the electron has a mass of 9.1 times 10 to the negative 31 kilograms. When your masses become small, that's when your de Broglie wavelengths start to become more appreciable, and your velocities, when they increase, then your de Broglie wavelengths become appreciable. So let's just look at that solution real quick. Yeah, you can see that the de Broglie wavelengths for the car and the smoke particle are like 10 to the negative 39, 10 to the negative 34, because the mass in the denominator is large. When you do the same with an electron, the electron has a small mass, right, 10 to the negative 31, and that's the reason why these things end up having a de Broglie wavelength. It's also quite small, but not as small as these other ones. The de Broglie wavelength for a 12 keV electron turns to be close to be the atomic dimensions. All right, the next question was on the Heisenberg uncertainty principle. I want you to understand conceptually what the Heisenberg uncertainty principle is, and also be able to do a simple calculation. Reason why the Heisenberg principle is important is because it underlies the whole basis of quantum mechanics. In quantum mechanics, the most important concept was that we don't know the precise location of an electron. So what we do instead is that we solve a function that gives the probability of an electron being in a specific region, a probability density function. And that's what the wave equation is. The wave equation is a probability density function that describes the probability of finding an electron. We find the wave equation by solving the Schrodinger equation. All right. So the next problem here is, this was on the, we have a parallel plate capacitor, and then we're accelerating an electron. The key concepts in this problem is that a parallel plate capacitor is supplying a certain amount of potential energy, electrical potential energy. We talked about gravitational potential energy in Newtonian mechanics, just for comparisons, and then we compared that to electrical potential energy in the electrical domain. I can pull up that slide real quick.
While you do that, I think one of the problems I had with that homework problem and the preceding problems was knowing when to, just inherently knowing when I want to end in joules versus when I want to end in electron volts. Is there like a rule, a general rule that could help us at the beginning of a problem?
Oh, like which units to use?
Yeah.
Well, let's look specifically at this problem. Number 5.
Yeah, and I think it was the ones after that too, but at least number 5.
Okay. All right, so this was just to get everyone on the same page here. In number 5, you have a parallel plate capacitor like this with a distance d, and so you place a negative charge here, and because the electric field is pointed from top to bottom, this particle is going to get accelerated towards the top. So David's question is about the potential energy. And actually this particular question is asking you to calculate the energy in both joules and electron volts. So this part is probably not a problem. This next part is asking you to calculate the force, the potential and kinetic energy. It's asking you to calculate. Okay. So in these types of questions, if you provide the answer in electron volts and I expected joules or vice versa, if you provided a unit of energy, then technically you have the right answer. If you provided it in the different units than what I was expecting, but the numbers are appropriate, the magnitude is appropriate, then I won't hold that against you. That being said, using certain units does make the calculations easier. So, for example, if there's a rule of thumb that we often use, is that the volts is a unit of voltage, right? And electron volts is a unit of energy. There's a nice, in these types of situations, when you have a parallel plate capacitor, there's a nice correlation between volts and electron volts. And here's what that correlation is. If I say, like, okay, we put, how much voltage do we put over here? We put 10 kilovolts. The voltage that we put across this plate is 10 kilovolts. Well, guess how much potential energy that corresponds to?
10 electron volts. 10,000 electron.
Yeah, 10 kilo electron volts. So if I put 10 kilovolts across here, kilovolts being a unit of energy, and I put a single electron in there, the amount of potential energy that electron has is 10 kilo electron volts. So that's where using electron volts might make the problem easier. So whenever we have acceleration systems, if like a scanning electron micrograph, for example, the systems will advertise that this is a 10 keV system. This is a 1 mega electron volt system for use that are used in other particle accelerator type things. Both systems are basically accelerating electrons to a fast velocity, but they don't tell you, they don't advertise that we can. Their system spec doesn't say like we accelerate to this much velocity. It says this is how much potential energy is being applied. They say this is a 10 keV system or 100 keV system. And if you know what that is, if you know that it has, if this was a let's say a 10 keV system, as it happens to be in this problem, the electron has 10 keV of potential energy at the beginning, and after it gets to this side of the plate, when it has passed through the system, now it has 10 keV of kinetic energy. That potential energy has been converted to kinetic energy, and so that's a really straightforward way to find the problem. So we know that the electron, by the time it gets to this side, it has 10 keV of kinetic energy. And from there, we can calculate the velocity pretty easily.
I think what you said, that voltage is voltage and electron volts is energy, I think that kind of helped, because I was looking at electron volts kind of like voltage.
That's the thing. It confuses students every semester.
Yeah.
Electron volts, it's a weird choice of units, and they use it because it has this nice correspondence. But don't get confused that electron volts, it's not a voltage. It's not a unit of electrical potential. It's like a joule. It's another unit of energy. The conversion between the two is 1 electron volt is a very tiny unit of energy. It's 1.6 times 10 to the negative 19 joules. Okay. To go further with your question, if, as you know, in the module 3, when we started drawing energy band diagrams, the units that we use in our energy band diagrams are pretty much always electron volts.
Mm-hmm.
Right? For these types of problems, we do switch back and forth a little bit between the two.
Okay.
But I won't penalize you if you give it in a different unit system. It's just to make it easier for you. All right. Force will always be given in newtons, and velocity, of course, in meters per second. So just to really drive this concept home is this last part here. Suppose we increase the distance between the plates by a factor of 10. How would this impact the final velocity of the electron? Now the key point here, okay, this problem says that we put 10 kilovolts between the electrodes, right? We have a 10 kilovolt between the electrodes, so that corresponds to a 10 kilo electron volt energy, potential energy. And that energy, as the electron moves through the system, is converted to kinetic energy. So by the end of the system, the electron has 10 kilo electron volts of kinetic energy. If you take the electrodes and you space them apart much further, but you didn't change the voltage, the electron ends up having the same potential energy. The potential energy is being determined by the voltage, not by the distance. What you might think, what sometimes mixes students up, and this is a subtle but important point, when you increase the distance between the plates, what happens to the electric field?
Nothing.
The electric field actually changes. It gets smaller because the electric field is V divided by the distance between the electrodes. The units for electric field is volts per centimeter. So the number of volts that you apply between the two electrodes divided by the distance between the electrodes. So by taking the electrodes further apart, you're creating a smaller electric field. Smaller electric fields mean, how's that going to change the force exerted on the electrode? It's going to reduce, right? Force is equal to the electric field times the charge. F equals EQ. So if you reduce the electric field, you're going to reduce the force on the particle. And so that's what might make you think that, hey, there's less force on the electric field, on the electron, so I'm probably not accelerating it as much. But here's the thing. When you increase the distance between the plates, you're applying less force on the electron, but there's also a larger distance for the electron to accelerate. So in this situation where you had the 10 kilovolts applied between a very small distance, there's a large force on the electron. The electron gets accelerated very rapidly over a short distance. And so it has 10 keV of kinetic energy at the end. You do the same thing with the plates spread further apart. Yes, there's less force on the electron, but the electron has more time to accelerate, and it still acquires 10 keV energy by the time it gets to the end. So that's the difference. It's the, you know, when we're talking about potential energy and kinetic energy, it depends on the voltage. All right. Okay, so that was about key concepts in this problem 5. Problem 6, a scanning electron microscope. Any questions on this one? Let me ask, how were the homework problems? Was it like, you know, on a scale of 1 to 10? Were the homework problems difficult? Difficult.
It took some like figuring out, but I think it's like maybe a 6 or 7.
6 or 7? Okay, how many people feel it's in like medium hard, like 5 to 7 range? How about like 8 to 10 range? How about below 5? All right, so it's a medium difficulty. Okay. But now's your chance. You know, if you guys have questions on how to do these problems, now's the time to go over them. So problem 6, the key concept there was that you're trying to get the electron to have a certain de Broglie wavelength. So we can control the wavelength by having it at a certain kinetic energy. So we have our voltage generator. The voltage generator is going to cause the electrons to accelerate to a specific kinetic energy. That kinetic energy corresponds to a velocity, and from there you can figure out the de Broglie wavelength. Okay. In general, just remember as a rule of thumb, like the more energy that a particle has, the smaller the de Broglie wavelength will be. Okay, now this problem uses the solution of the Schrodinger equation in a one-dimensional potential well, and then we're just plotting it and calculating the electron energies. So with the Schrodinger equation, there's, you know, obviously I'm not going to ask you to to plot a function with MATLAB, because you're not going to have access to MATLAB, but you know, I might actually ask, you know, a fair question could be like, I could just ask for qualitative, you know, qualitative lines describing what the solution might look like. You know, just to test a qualitative understanding of what a solution of the Schrodinger equation may look like. This is the Schrodinger equation in a one-dimensional potential well. One of the key concepts that we learned with the Schrodinger equation is that there are multiple solutions to the Schrodinger equation. And this is what solution 1 looks like in the blue line. Solution 2 looks like this. Solution 3 looks like this. Okay. The fact that you have multiple solutions to the equation, that's called a situation where you have eigenfunctions and eigennumbers. That's what the mathematicians call it. But when we're talking about how it relates back to the electrons, there are multiple wave functions. Multiple wave functions, each wave function corresponds to a state that the electron can be in. So if there are multiple solutions, that corresponds to multiple energy states for the electron. So an electron could have this wave function here, which is in blue, and that wave function is associated with a certain energy. An electron of higher energy might have a wave function that looks like n equals 2, and even higher energy, n equals 3. The higher numbered solutions, the higher eigennumber solutions, correspond to higher energy states, and they usually are higher frequency solutions, as you can see here. The physical interpretation of something like this means that this tells you the probability of where to find the electron. So you have to take this function and square it. This is what psi squared looks like. And so for an electron that's in energy state 1, the electron will most likely be in the middle because that's where the probability density function is the highest. Whereas something in n equals 2, you can see the orange line, it has 2 humps here, here, and here. So the electrons are most likely to be in this region or most likely to be in this region. Okay. So those types of conceptual questions I think would be fair game for the test. In terms of quantitative calculations, the energies for the electron states, so the solution to the 1D Schrodinger equation is something that I could expect you to know. I will not, obviously I will not give you like an unknown boundary problem and ask you to solve the Schrodinger equation and find the solution. That's something that...
Derive the equation.
Yeah, that would be very difficult. I think I would fail the exam if I did that. But the key concepts is the things that I would like for you to be able to do. This next question, I don't know if any of you had a chance to look at the solution or try it yourself, but when you start getting into two-dimensional functions, they have like, you know, the Schrodinger equations, the solutions to the Schrodinger equations start to look something like this. It's pretty neat. So you can see these are also oscillatory functions. You know, this is a low value and then this is a high value. So they just have like, it looks like a two-dimensional wave, and the high and low points of that two-dimensional wave tells you where the electrons are in a two-dimensional space. And then in a three-dimensional space, which is the real world, they also have these like oscillatory or sinusoidal type functions. Yeah, so these are, you know, this is in 2 dimensions. The electron would be very likely to be right in the middle here. If it's in the lowest energy state, if it's in the next lowest energy state, it would likely be in the middle of one of these 4 quadrants, and then so on. At the higher energy states, you have similar relations. There are additional locations where the electrons are more likely to be. So they just get more and more complicated from there. Number 8. So I'm moving on now to the next question. This is a very simple question that requires no calculations. That I would be expect you to be able to do is just to draw this type of diagram for an atom that I give you, and indicate the shorthand electronic shell structure for certain atoms. Okay. This question was on the Bohr radius. Question. Oh, I didn't have this. Did I have? Yeah. I have the solution for problem 9. Did I include problem 9 in the homework?
No.
Okay. Then I won't ask you about that. Yeah, I won't include that on the test. All right. All right, so that's module 2. Let's get into module 3 now. That's some homework here. All right, so let's start with questions from okay. What are the challenging parts you had on homework 3? Have a second to look over your homework problems if you need to.
So I had a question.
Yeah.
I think it was probably 4.
Yeah. Sure. What's up, Trevor?
Yeah.
Mhm.
So in your solutions, you had the approximate way to do it, which is to assume that 10 to the 18th is your concentration of electrons, and then use that and Ni squared to calculate concentration of holes.
Mm-hmm.
But then you had like a more accurate way of doing it.
Yes.
Which was, just get the quadratic equation and solve it.
Yeah.
What are you expecting on the exam for like a question?
That's a really good question. All right.
I think you pulled out the wrong solution.
Yeah.
Oh, my bad.
Homework.
Homework 3 solutions. There we go. Thank you. Okay. All right, so the wafer above is additionally doped with arsenic atoms. So what we started off with, we started off with a wafer that was doped with 10 to the 17th, but it was doped N-type. I'm sorry, it was doped P-type. Yeah. So question 3, we had a P-type doping of 10 to the 17th, and this is a typical, this is a typical thing that comes up in semiconductors. So we start off with, I think there's a way that I can add to this. There we go. There you go. So I mentioned this in class also, but like a common situation that comes up is that you start off with a P-type wafer. Let's say this was 10 to the 17th. Yeah. And so what we do is we might take a region here and we want to make this N-type, right? This is one way to make a diode. And so in order to make this material N-type, the P-type material is first made using using a process. The entire wafer is P-type, let's say. Does anyone know how we make the P-type? That's actually fair game for the test. What's the method that's used to make silicon wafers with a specific doping, uniform doping? And if you don't remember the name of the process, that's okay, but conceptually what's being done. So when we're making, like, think back to originally you get your silicon, silicon comes from sand, right? What's the next process when you're making a silicon wafer?
Melt it down and make an ingot.
That's the one, yeah, the melting down. That's called the Trotsky process. All right, do you guys remember this?
Yeah.
Okay, good. You scared me for a second there. So you take the silicon, you put it into a melt, and then when you melt it, you can actually add your dopant atoms at that time. And then you pull out a seed crystal. The atoms add to that seed crystal, so it forms a nice crystalline structure as you're slowly pulling it out of that hot melt, and you end up with a big tall cylinder that's called an ingot, and it's all single crystal silicon. So now you've created that, and you slice it up, and you slice it up into small wafers. So that's how we got this. This is from the ingot. And when we want to make the diode, we use another process where we diffuse materials in there. So we'll put this in a chamber that has arsenic ions or other column 5 elements, and we'll block off certain regions. Okay, don't worry about the details of this yet, but we block off certain regions so that the gas molecules can only diffuse into certain regions of the wafer. And when those arsenic atoms diffuse into the wafer, they are impurities, right? They're column 5 dopants, so they create an N-type region within the P-type silicon. So that's what selective doping is. In order to get that to work, conceptually, this is in the notes too, but I just want to mention this again, is that if you have a boron impurity like this, and then the silicon atoms around it, okay, remember the boron atom creates a hole, so this is a hole. Now, if you come in and then you dope another nearby region, let's say you dope, let's say you dope another nearby region with arsenic, and the arsenic has an effective positive charge, and it also comes with an extra electron, right? For let's say you doped at 10 to the 17th boron, okay, so it's p-type, but then you added 10 to the 17th arsenic. What's going to happen?
Recombination.
The electrons, the extra electrons will find the holes, and then you'll end up with you'll basically cancel out the two effects, or you'll end up with a material that has like intrinsic like properties. But in order, if you dope it 10 times higher, if you dope it at 10 to the 18th instead of 10 to the 17th, now what happens? The material actually, you have 10 times as many extra electrons than you do holes. So the material becomes effectively n-type. So that's what this question is really about. Now, so getting back to Trevor's question, your question was like, can we use this approximation or do we have to use the quadratic formula? So here's a rule of thumb, if it is 10 times greater, if the doping density is 10 times greater than the original doping, then you can just approximate. So the approximation is basically what I said earlier. If I dope it at an order of magnitude higher, like 10 to the 18th versus 10 to the 17th, then we can basically assume that we can ignore the number of boron atoms that are already in there, and we can just say this is now an n-type material with an effective doping 10 to the 18th. We can ignore what was there before. But let's say we doped it at similar or equal doping, like let's say we did 2 times 10 to the 17th instead of 10 to the 18th, if we doped at 2 times 10 to the 17th, which is only a 20% difference, or 200% difference, which is still like, it's not a 10-time difference. Then you have to use these space charge neutrality equations. And this is also in the notes. The space charge neutrality equation, is basically saying that the amount of positive charge is equal to the amount of negative charge. So a hole has an effective positive charge. A dopant ion, so an arsenic ion like this has a positive charge. And the same thing goes on the other side. The electrons have a negative charge, and the acceptor, the boron ions, also have an effective negative charge. So this is one equation. So this is, you need a second equation, NP equals Ni squared. So now you have two equations, two unknowns. You're trying to figure out the hole and electron concentrations, and you can find it from there. All right, that's obviously more involved, but you can see that they both give you similar answers. Our approximation gave us a hole concentration of 225 per centimeter cubed, and then if we did the whole quadratic equation, we get 250. So it's off by, like 15% or so, which is not bad for engineering.
So essentially, low-level injection and high-level injection we can approximate, but if it's kind of in that sweet spot in between, we more than likely should do the actual equation?
Yeah, if they're similar.
Okay.
Right. Exactly. All right. So getting back to Module 3 homework. Other questions?
Professor, just like in question 7,
Mm-hmm.
you mentioned that the unit should be in MKS for mobility.
if you want some specific units like that, would you mention on the test, or do we have to know that they should be the specific units for the test?
I will mention to you if there's specific units that I want. Yeah, like this particular problem is that this was actually a hint that I was giving you, because this is given in the effective mass is given in kilograms. I was suggesting using MKS units here. Yeah. Number 8. Suppose we are doping the wafer so it is n-type. Show that the minimum conductivity occurs when n equals ni times mu p over mu n. All right. Yeah, this is an interesting question. Let's look at the solution here. So we're doping the wafer so it is n-type. Show that minimum conductivity occurs when n equals mu p over mu n. This is like a little mathematical trick.
So on
Oh, I'm on the wrong module. Sorry. I guess this problem was talking about that the fact that when you dope silicon, you are changing the N and the P concentration both, right? So when you increase the electron concentration, the hole concentration goes down. So you're affecting both types of carriers. This is the equation for conductivity. So the N, when you change the doping, N is affected and the P is affected. All right, so they're asking, the question that's being asked is that at what electron concentration do you get the minimum the minimum conductivity? So I don't expect to have a question like this on the exam, but this is just minimizing this conductivity function. If you want to minimize the conductivity function, you would want to have find where the slope of the function is 0. You know, like it's a slope where the slope is 0. Wherever the slope is 0, it's either a global maximum or a local maximum or local minimum. So that's why you're finding the derivative of it, and you find where that where the slope is 0. So these are two equations with two unknowns. Let's see, n equals ni squared.
Divide by n, then
Yes. So this is one of the equations that you have, and the second equation that you have is n equals ni squared. So what you're doing is you're plugging in np equals ni squared so that your conductivity equation, notice.
Excuse me.
Yeah.
I'm sorry. Sir,
No problem.
I'm looking for this person in your class.
Yeah. Oh yeah. Sri.
Is she here?
Yeah. Okay.
Is this yours?
Yeah.
All right. You know where you left it, right?
Yeah.
Okay. There's your credit card. I didn't charge too much.
Wow. You're a lifesaver. Thank you.
So you were in trouble, huh?
That could have gone one of two ways. It turned out the good way. All right. Good. Glad you found your phone. Yeah. So what we did here, we had this is the second equation, np equals ni squared here. So we substituted this in, so now our conductivity equation is just a function of one variable, just a function of n. And then we minimize that function by first finding the derivative, setting it to 0, and finding the value of n at which the derivative is 0. All right. So yeah, like a lot of the thing here is just a mathematical type thing, but conceptually what's happening is that when you change the electron concentration, you also change the hole concentration. So you have to consider both elements when you're looking at conductivity. Most of the time, I should say most of the time, you're going to be working with N-type and P-type materials. So what happens to this equation if you're working with an N-type or P-type material? Just want to make sure you all know that.
And if you're working with just N-type?
Yeah, if you're just working with N-type,
Yeah.
then exactly, you just include this term. You don't include the second term. And vice versa. If you're working with a P-type material, then you would just include this term. That simplifies your calculations. You know, there's one less calculation that you have to do. All right. Question 9 is not going to be on the exam, so don't worry about that.
There's no solution for it anyway.
Right. I mean, like it's Appendix 3 in the text. I realize many of you probably don't have the text.
What?
I lately, like the last few years, I've just been like making my notes so that students don't necessarily have to buy the textbooks. You can get by without it. If it's helpful for you to have the extra, extra notes, I didn't mention this at the beginning of the semester too. I welcome you all to purchase a textbook if you like, if you want to have the ability to read more on a certain topic, and if you don't get what I'm saying. But like I just stopped requiring it because it annoys me that textbook vendors charge $150 a book. That really bothers me. Education should not be that expensive.
Can we discuss question 5 real quick?
You would like to or not?
Can we go over it?
Okay, sure. A typical microprocessor is fabricated from a P-type silicon wafer. Why does a microprocessor no longer work at high temperatures? All right. So there's a few different things here. So let's just start with the solution here. There it does cover the two aspects that I was thinking. Okay, so the two mechanisms that I wanted you to understand that are temperature dependent, relevant to microprocessors are one is at really high temperatures the material becomes intrinsic. So that's the first that's the first part of the question. So you have a P-type silicon, right? And you have the band gap. So at really high temperatures, the electrons in the valence band have enough energy to go up into the conduction band. So when that happens, then your entire material starts to become conductive. That's that intrinsic region that we talked about in this section of the slides. Here, let me just pull up that section of the notes here. This is the slide I'm talking about. All right, so we're talking about here. This is a temperature range where you want to use your semiconductor. Okay. This example is for an N-type semiconductor, but the same would apply for a P-type. You want to be at a temperature where there's enough energy for the dopant ions to go up into the conduction band so that you have a proper N-type material. So there's enough energy for small energy transitions like this to happen. You don't want the system to be at such a high temperature where this energy transition can happen, the one going across the band gap. Because if that happens, then electrons in the valence band are going to jump up into the conduction band. And now you're going to have this situation where your entire material becomes conductive everywhere.
Like metal.
Yeah. You don't want that to happen because the way microprocessors work, you actually want certain regions to be conductive and you want other regions to be non-conductive. If you're using silicon everywhere, and you're using a really, really high temperature, then everything becomes conductive. So if I told you that the wafer was N-type, the answer would be the same. At high temperatures, it becomes intrinsic, intrinsic-like properties. And the use of the word intrinsic is a little bit confusing because intrinsic implies low carrier concentrations. But this is what they call it intrinsic, because if you took an intrinsic material, an undoped material, and you put it at super high temperatures, then the same effect would happen. Does that answer your question?
Yeah.
Okay. Now the second part of it is actually practically more important. Practically speaking, it's more important because the second effect is the resistance effect. So that happens at temperatures like 200. This effect here you'd have to be at really high temperatures. So you'd have to be at like
I think the 2 is at 500 Kelvin.
Yeah, that would be 500 Kelvin and above. So 500 to 1,000 Kelvin, you start seeing that type of effect. What happens even before that, when you're at let's say 200 Celsius, right, or 150 Celsius even, you start seeing another effect happen. Does anyone know what that is?
Slower mobility.
Lower mobility, right. Lower mobility because of what?
Thermal scattering.
Yes, lattice scattering, right. So there are two types of scattering mechanisms that we talked about. One mechanism becomes significant at high temperatures. Another mechanism becomes significant at low temperatures. Impurity scattering becomes significant at low temperatures. Lattice scattering becomes significant at high temperatures. So silicon operates well at room temperature, but when we go from room temperature just 25 C, we go up to 100 C, then we start to get these lattice scattering effects that become important. Lattice scattering, it decreases mobility. So one way you can think about it is that the electrons are just not moving as fast through your material. And if your transistor circuits are working under the expectation that the electrons are traveling through your transistor at a certain speed, then your whole system stops working. The only way to get around it is to slow down your clock speed. Slow down your clock speed so that your transistors can have time for the electrons to move through. And there are systems that do that. You might notice that your computers actually work slower when they still work. They just turn down their clock speeds at higher temperatures. So that's one way to think about it in terms of mobility. If you've taken a circuits class before and you like thinking about things in terms of time constants and transient response, in transient response, one of the first things you learn about is that you learn about an RC time constant, right? Like the time constant is 1 over 2 pi RC, where R is the resistance and C is the capacitance. So the capacitance is not what's changing here, but the resistance. If you increase the resistance, the time constant is 2 pi RC. It's proportional to 2 pi RC, not 1 over 2 pi RC. Higher resistance means slower time constants, longer time constants. Okay, and so that slows down the time response of your circuit. Okay. Moving on then.
On number 3, the question G, you use different value for the mobility. One 400, and the other time you used 450.
Calculate the conductivity of the material and also calculate the conductivity of intrinsic silicon. How do the two compare? Okay.
The first question we put the mobility 400, other one 450.
It's question 3, part G. This part here?
Yes. Yeah, here we put it 400.
And in the earlier parts of the question, we use 450?
The next one. It's going to be after this.
In part G.
Yeah.
Oh, part G, I'm sorry. Moving up and down a lot.
450 and we use 400.
Oh. I think that was a mistake on my part. I should have used the same. Mobility for both.
Because it's always mostly 400.
Yeah. Mostly it's 400. Here's the thing. So I'm gonna give you a chart of doping versus mobility, and you've seen this chart in your notes.
Can you show us how to utilize that chart again?
Yeah, I can do that. Let's make this bigger. All right, so this is the chart that I would generally give you on a test. Rather than, I can give you the constants, the mobility at room temperature of intrinsic silicon. But most of the time you're going to be working with doped semiconductors and where the mobility is a function of doping. So you have to be able to look up on this chart what the mobility is going to be. Now, because this is a log scale plot, and even when I look it up on this plot, I sometimes have a hard time telling whether the difference between 400 and 450. So just estimate, and I'm not going to hold that. I'm not going to hold that against you. If you're like way off, if you say it's 1,000, then I'll be like, wait a minute, you're not reading this chart properly. But if it's 400 versus 450, it's not a big deal. I mean, like I made a small mistake there too. Now let's look at these chart though. Let's make sure that we understand this. Getting to DeMarco's question also. This is showing a doping level on the x-axis, 10 to the 14, 10 to the 15, 10 to the 16. So this is the level of doping of, like whether it's p-type or n-type doping, it doesn't matter. You look at the doping level on the x-axis. And notice that this is a log scale. All right? And this is the mobility, also on a log scale. All right? What is the reason reason this mobility goes down at high doping? What's the physical reason for that? Well, what does mobility depend on?
Scattering.
Yeah,
Scattering, right?
Impurity scattering.
What are the two mechanisms of scattering we know about in this class? Impurity and lattice, right? Lattice is not doping dependent. Lattice is temperature dependent. Impurity scattering is doping dependent. So impurity scattering is the reason why the mobility goes down here. Okay. Now, if you look at this, you'll also notice that this thing starts to flatline when you get to the left. So the chart is only showing as low a doping as 10 to the 14th. Once you go below that, 10 to the 13th, 10 to the 12th, whatever, you can just assume that this line continues on as a straight line forever. All right. Now, the last part DeMarco is asking is, how do you read this chart? This is a log scale, but it's a little bit confusing in the sense that instead of putting, on a log scale, the scale normally goes, it'll be 1 times 10 to the 2, and then the next hash mark will be 2 times 10 to the 2. The next hash mark will be 3 times 10 to the 2. In this chart, they only have hash marks every alternate one. So this is 1 times 10 to the 2. There's 2, 4, 6, 8, and then 10. So this is 2. This is 4. This is 6. This is 8. And then this is 10. Okay, so in this particular problem, what we're doing, we said that we were at 10 to the 17th, right, Mama? So 10 to the 17th, what is a mobility of holes? You go to 10 to the 17th, you move down here, and mu p is right about here, so you move across here like this, and you can see that it's approximately here. So approximately 400 centimeters squared per volt second is the units. All right. Next question. see some final things about Module 3. Yeah, like I said, this is the type of question that you'll almost certainly have on the test. Is something like this, where I give you a doping of a silicon wafer, and then I ask you to calculate all this stuff. Draw the energy band diagram, figure out the concentrations, figure out the resistance. That's a very practical problem. I think that all of you should know how to do something like that. And in Module 3, if you'll recall, that there were a lot of discussion type questions that we did in class. These are the types of questions, these are the types of conceptual questions that I would give you on the exam. They wouldn't necessarily be multiple choice, but they would be concepts like this. How does this concept link to this one? The kind of stuff I'm asking you during the class too. All right, moving on. Let's go to Module 4. So I would say the homework on Module 4 was probably the longest one. Has everyone gotten a chance to get through the homework in Module 4 yet? Good. Okay. All right. So this was probably the most involved homework set of all of them. So let's go over questions here. Question 1D. Okay.
B.
1B?
B and D.
Okay. Well, then maybe we just go over the whole question then. We have N-type semiconductor with a certain doping. We irradiate it with laser light, and in this case, you are being given how many electron hole pairs it's being generated per second. You turn off the laser, and then you're asked to calculate these excess hole concentrations at different times. So, what are some of the key things we want to note here? You're irradiating the entire silicon wafer, okay? You're not irradiating specific parts of it. So, if you're irradiating the entire thing, then that narrows down the problem, and it tells you that this is not a problem where you have spatial gradients. There's no spatial gradients, there's just a temporal. It changes with time. Carrier concentrations change with time. That's the first thing you want to notice here. The second thing is that you have a laser source that's giving you a certain number of electron hole pairs per centimeter cubed per second. So that is, what does that equate to in the equations that you're familiar with?
Delta N and delta P.
Yeah, that can give you your delta N and delta P. Exactly. Good. All right. So let's go through the solutions then. All right. So this number that was given to you, 2 times 10 to the 23rd electron hole pairs per centimeter cubed per second. That is the GOP. That's the carrier generation rate that you're given in this equation. I skipped over this, but this should be straightforward by now. If you have, if I give you N-type or P-type doping, you should be able to calculate the electron hole concentrations. So that's easy. And N0 is just equal to the doping, and then P0 you use NP equals Ni squared. Use that equation, you get 225. So that is the N0 and P0. Notations are important here. N0, whenever you have that 0 subscript, that means before you turn the light on. N0 and P0 are the electron levels at that point. Then the excess, so sigma n and sigma p, those note that they're equal to each other, because when you're shining light on the material, you're creating those excess electrons and holes in pairs. Sigma n is equal to sigma p is equal to GOP times tau p. All right, this is the generation rate, which you're given here, and you're also given the carrier lifetime, which is 15 nanoseconds. All right, so the units here, this is electron hole pairs per centimeter cubed per second, and then this is given in seconds. So those cancel out, and you're left with 3 times 10 to the 15th per centimeter cubed. You're shining light on the material, you created excess carriers. All we did was calculate the excess carriers in part A. You're also asked to calculate the total. The total electron and hole concentrations are the original amount before shining the light on the material, added with the excess that you added by putting light on the material. And what you notice here is that N0 is equal to 10 to the 8th. N is equal to 10 to the 8th. So after shining light on the material is 10 to the 18th. Sorry, not 8th, 10 to the 18th. Before shining light on the material, it was also 10 to the 18th, right? So fractionally, like percentage-wise, the electron concentration didn't change very much. The electron was a majority carrier, and the majority carrier didn't change by a significant fraction. So what is that called when we do that? Low-level injection. Got it. Right, exactly. The minority carrier concentration, on the other hand, it changed quite a bit. It changed from 225, so it's very low before shining light, and then the excess carriers created an additional 3 times 10 to the 15th. All right, so that's A. That's not what the question was on. Let's go to part B. Calculate the excess and total concentration of electrons and holes at T equals 2 tau. So this is where you need to use this carrier lifetime equation. This one here. All right, conceptually what's happening, like you turned off the light at a certain time. Right? You think in your head about the 4 carrier processes that are happening. When you turned off the light, you're no longer generating carriers from the light, right? Is there diffusion and drift happening here?
Yes.
No, there's no concentration.
Exactly. Subtle but important point that we shine light on the entire material, not a portion of it. We shine light on the entire material, so there's no concentration gradients. Concentrations are the same everywhere. Excess carrier concentrations are the same everywhere. So there's no diffusion. Is there a drift? No, because there's no electric field. Okay, and recombination, the 4th process. Yes. There were excess carriers generated, and those excess carriers recombine. Those excess carriers basically disappear over time. That's what's happening in this problem. When you turn off the light, the excess carriers die away. But it doesn't happen instantaneously. There's a certain decay time constant. Right? And that decay time constant is the carrier lifetime. So that's why it's described by this equation here. You can look at the slide on it that's in the notes, but I'm just trying to be expedient with time here. So this is saying that the excess carrier concentrations is going to be this exponential function of time. It's a decay function, negative t over tau. The tau describes the rate. And delta n is the initial amount. The initial amount of excess carriers, the sigma n, sigma p, is 3 times 10 to the 15th. Multiplied by e times e to the negative t divided by tau. The tau is equal to 15 nanoseconds. But what I'm asking in this question is that the t is equal to 2 times tau. So the numerator here is equal to 2 tau, and the denominator is tau. Right? The taus cancel, and you're just left with e to the negative 2. And so that's where this 4 times 10 to the 14th comes from. Now, if I did this, I would mark myself points off because I didn't give the units here. Remember to include units in your when you do the exam answers. All right, so this is the change in the excess concentration, and then the total, just like before, you can find the total by adding the initial amount plus the excess. All right. And the same with 3 tau and so on. All right. Now this last part here I think is good to know is how long will it take for 99% of the carriers to recombine? So you want, here, let me add something in here. So the question is asking how long will it take for 99% of the carriers to recombine? So that means, your sigma n is going to be 0.01 times the initial sigma n, so sigma n 0. Sigma n 0 is the excess carrier concentration right when you turned off the light. And we know that the excess carrier concentrations are going to die out with time, right? So we want to find the time at which the sigma n is equal to 0.01 times sigma n 0. All right. So we want to set up this equation: sigma n equals sigma n 0 e to the negative t over tau. And with this ratio, sigma n is equal to 0.01 sigma n 0. So then this becomes 0.01 sigma n 0, but that's what's on the other side that cancels. So you're just left with 0.01 e to the negative t over tau. So you're trying to figure out at what time t does this exponential equal to 0.01. And if you solve for that, you get a ratio of 4.6 tau. So 4.6 time constants. Within 4.6 time constants, 99% of the carriers are gone. So in this particular problem, the time constant is 15 nanoseconds. So within 15 times 4 nanoseconds, within 60 nanoseconds, 99% of the carriers are gone. Right. So you could have a similar question on the exam. All right. So that was problem 1. We're starting to run out of time here. Conceptually, the difference between problem 1 and problem 2 is that problem 1 was an example of a temporal change in excess carrier concentration. The excess carrier concentration is a function of time. In problem 2, the excess carrier concentration is a function of x, the location. Right? That's the difference between the two problems. So if we compare and contrast the two types of problems, we actually in both cases we get exponential distributions. In the temporal case, at the one we just did, the carrier concentration is an exponential function. It's an exponential decay function of time. And that means that the excess carriers are disappearing over time. And the time constant, it was t over tau. Okay. So this one was sigma n equals sigma n 0 e to the negative t over tau. Now in this problem, what you find out is that this is a spatial distribution, and this is where your sigma n is equal to some delta n times e to the negative x over LP or LN, depending on which type of carrier that you're talking about. You see, it's also an exponential decay function, but it's a function of x instead of t, and the rate constant, instead of being t over tau, it's x over LP. Does anyone remember what LP is?
Diffusion length.
The distance when they can recombine.
Exactly. So you're both correct. It's LP is a diffusion length. LP is equal to the square root of dp times tau p. It's the average distance that a carrier travels before it recombines. And if we look at this problem, we don't have enough time to go over all the problem, but conceptually what's happening here is we are irradiating light on a portion of the material. So that area of the material is generating, excess carriers are being generated, but outside that material we are not shining light. So there's a carrier concentration gradient. So which of the four processes occur here? Generation is happening. Generation is happening. There's diffusion. A drift is not happening because there's no electric field, but recombination is also happening. Right? So carriers are being generated here. They are diffusing out this way. They're diffusing out this way. And then when they diffuse out, they eventually recombine. So LP is the average distance an electron or hole diffuses outwards before it recombines. This tau was the average time an electron or hole exists before it recombines. All right, and they're both exponential rate constants. All right. So you have more questions about that? I'm happy to answer any of your questions if you email me, or if you'd like to meet with me also. I should be available tomorrow, a good chunk of the day. Friday I'll be available by email, but I won't be on campus. I have a meeting in the morning, and then I'm going to be gone in the afternoon. If there are questions that if questions come up, best thing is to meet me tomorrow, and after that I'll be available by email. All right.
So till what time will you be available?
Tomorrow?
Yeah. What time?
I can make myself available as long as you need. You know, like if you're only available in the evening, I could come back. You know, I could come back and meet you in the evening. If coming down to campus is a problem, like we have video chatting capabilities through Skype at Wayne State. You know, like there's I don't know what they call it, like Skype for Business, or what do they call it now? They call it Teams or Microsoft Teams. Anyway, the point is, like, if any of you have difficulty making it to campus and you'd like to go over something, we can meet over one of the video shares too. But let me know. But just like Friday and Saturday, I'm going to be busy, and then Sunday I'm traveling, so I'll only have email access at that time. But I hope this review session was helpful. So again, one page of notes front and back, calculator, and I'll see you here at 5:30 Monday.
Thank you.
Okay, great, thank you.
Could you, Professor, I emailed you about